Thank you for the introduction. So let me now explain you why these talks should be interesting to you. So the mutual information, probably well familiar to all of you. It's a very important information-theoretic concept. And it's subtle, it's non-trivial to estimate. In this section, in this talk, I would like to discuss known difficulties and provide some, well, kind of known solutions, or at least solutions you could have derived if you read some of the published papers. Those of you who are familiar with my talks, with my previous talks, probably know that I like to give very mathematical, very hard to digest talks. So rest assured, this one will be no exception. So just in case you fall asleep, like on the fifth slide, here's a TLDR, or like the more proper too boring didn't watch summary of the talk. So what I want you to take away from this lecture. First point is that if you seek to have a lower bound on entropy, then, well, not just some lower bound on entropy, but a very good one. What it means for the bound to be a good one, we'll discuss later. But basically, if you want to have a good bound that you would enjoy using in some practical application, then you can only have it when the entropy is small. When the entropy is large, then that bound is exponentially hard to get. It's exponentially costly. It's exponentially expensive for you. Consequently, since the mutual information is a kind of composed of entropies, the same sort of applies to the mutual information. You can't reliably estimate mutual information when it's high. Otherwise, it would again cost you the cost of such an estimation of such a lower bound. Actually, a lower bound would be exponential in the mutual information. This is obviously not something you would like to have. However, we can actually come up with some good lower bounds if we step away from the black box assumption. If we actually know something about densities, we would like to estimate the mutual information for about the random variables and their behavior, then things are much more easier. Now, you might not only be interested in lower bounds, but also in upper bounds. Lower bounds are good when you want to maximize something. Then maximizing the lower bound will eventually lead to maximizing the actual quantity you're lower bounding. But what if you want to minimize the mutual information? Then a natural thing to minimize would be an upper bound. Can we have good upper bounds? Well, turns out yes, if we know distributions. And the final thought is that, well, mutual information is not the only measure of dependence between random variables. Maybe some other measures will be easier to work with. And people have already made some preliminary research in this direction. We'll briefly touch on that also. So the mutual information, what is it good for? It has many different equivalent definitions. The ones I have here is just the difference of entropies. The mutual information between random variables x and z is equal to the difference of entropies. It's you subtract from the entropy of z the measure of uncertainty in the random variable z, the entropy of z conditioned on x, how much uncertainty there is left in z once you know x. It's a very intuitive measure of information. It also can be expressed in the terms of a well-known divergence, the Kullback-Leibler divergence, as the Kyle divergence between the joint distribution and the product of marginals. So its theoretic information interpretation is that it captures the amount of information one random variable carries about the other. It has this, sits here on this Venn diagram. So why should you care about mutual information? Well, its nice information-theoretic interpretation has led it to be a very useful tool, very useful measure in many practical applications. Like, for example, since we are all kind of interested in Bayesian deep learning here, you can use it to measure posterior collapse in latent variable models like VAE. It's a very natural measure that basically estimates that is equal to average chiral divergence between the true posterior and the prior distribution. If the true posterior deviates highly from the prior, that means that the model heavily relies on the latent representation, something you would like to have from the latent variable models like VAEs. Conversely, if this mutual information is equal to 0, if there is no relation between the samples from the generative model and the latent representation, then obviously you failed to learn your VAE. You could have just learned the explicit density model right away without any variational stuff. There has been a lot of applications in the representation learning community. Many works on that basically say that, okay, you have some complicated object X, and you are interested in learning a representation that captures as much information as possible, that basically encompasses all the knowledge there is in X. And this is done by saying that, okay, there is an encoder E theta, parameterized by parameters theta, and we want to maximize the mutual information between the original X and the representation obtained through the encoder. This is usually not the only objective, but is like a kind of a regularizer that says that you should that representations should be very informative. You might also be interested in control independence. That is, since mutual information is equal to 0 only if and only if the random variables are independent, then this is a good tool to enforce independence between random variables. One application for that is in fairness. For example, suppose you're like at a bank maybe, and you give loans to people. Well, you don't want to discriminate people based on their race, for example, or gender, because this would lead to social instabilities, social inequalities, and well, it's an unethical thing to do. But how can you actually guarantee that you are not discriminating based on these features? Of course, you would not include them in the model, but they can still sneak into your predictions. Maybe people of certain race tend to live in more poor regions of the city, and you have this geographical feature in your feature set. Or maybe through this information can leak through some other features that you don't know to be carrying this information. So a way to so this is called the demographic parity in this field of study. And the way to solve this problem is to say, okay, there is sensitive information C that we don't want our model to be using when it's making prediction Y for the input X. So we just want to enforce that there is 0 mutual information between the prediction and the sensitive information, conditioned on the representation X that we know about the people, that our model is using, conditioned on these features used for the prediction. It also can be used in uncertainty estimation. It has been used in famous, I guess, information bottleneck principle to analyze neural networks, and there are many more applications. So how do you actually estimate it? Well, if you actually know the densities, if you know both the marginal density and the if you know both marginal densities and the joint density, then things are easy. You can just form a Monte Carlo estimate. But oftentimes you don't have this full knowledge. Sometimes you don't know any distributions. You can only sample from the joint and thus from essentially from the marginals or from the marginals. well, then we are out of luck with the unbiased estimate of the mutual information itself. There are some estimators out there, but they are not guaranteed to be either unbiased or lower bounds or upper bounds. They are just some estimators. We would like to be more than that. We would like to have some guarantees. In particular, we'll be talking about lower bounds and upper bounds. So for lower bounds, I claim that you can basically split it in 4 different cases. So I guess just to remind you, I'll write down here the formula for the mutual information in large. So it's the joint density divided by the product of marginals, or equivalently, it can be written in this form. All right. So in this categorization, I consider 4 different defining categories that basically your ability to do efficient estimation boils down to whether you know or not the marginal distribution on Z and the decoding distribution on X.
By know, you mean having access to
yes, yes,
function.
yes. You can evaluate the density function. We always assume that you can sample from the joint and thus form samples from any of the marginals. So what I'm claiming is that if you don't know the marginal distribution of Z or X, they are kind of symmetric, but we will be talking about the marginal distribution on Z and conditional distribution on X, just to fix the particular ordering. So if you don't know the marginal distribution, then things are hard for you. But if you do know the marginal distribution but don't know the conditional distribution, then things are not as good, but still manageable. You can have good bounds there. Finally, if you know the joint, essentially, both the prior distribution and the conditional distribution, then things are very good. So for upper bounds, the situation is similar, but it's transposed. Now you need to know the conditional distribution, otherwise things are hard for you. But not knowing the density is not that punishable. So in a sense, you can see that these two are transposes of each other, and this is not a coincidence, of course.
Can you speak a bit more about the situations when you can, say, sample from the distribution but cannot compute it, or otherwise you can compute it but cannot sample from it?
Yeah, sure. For example, in GANs, the generator, basically the neural network that is fed some random noise and that outputs some samples, it is an example of implicit model. You can sample from it easily, but you cannot evaluate its density. And the vice versa, suppose you have a neural network that takes in an image and outputs single real valued number. You can say that this is an unnormalized log density.
I understand it, but how it will relate to these tables? So if you...
Oh, yeah, sure. So basically, the generator, the GAN generator, is an example of this category. Usually you know the noise distribution, the inputs to the generator, but you don't know the density of the outputs. Moreover, it's actually, it does not exist. It's like a delta function along some low-dimensional manifold.
I suspect the question was different. The question was what to do if you can evaluate densities but cannot sample. How this table will change. Always assume that we can sample from the joint. Because otherwise we will be able to get a reliable estimate for the integral.
Yeah, well, if you don't know how to sample, well, things are hard for you.
And well, we may always say that we could use at least XCMC methods.
Well, but then you pretend you can sample, right?
Yeah.
So, yes, we assume that you always can sample if you can find a way to sample and convince yourself that you are indeed sampling. Any other questions?
Where did you get this table?
This is like a summary of what's going to be told next. This does not follow from anything that I have told previously, but this will be following from what I will tell you in the next. It's more like my summarization of what's going on in the field. So, black box lower bounds. Let's get to the second point of the TLDR list, why black box lower bounds are bad. So the elephant in the room, let me present the black box lower bounds to you in the first place. So we know that the mutual information is equal to KL divergence. So we can, to come up with some lower bounds on the mutual information, black box lower bounds actually, we can just use black box lower bounds on the KL divergence, right? I wrote down two of them here. First one is called the Nguyen-Wainwright-Jordan lower bound. And it has this form. So f here is any unconstrained function. It takes in your sample x and outputs some real value. There is no constraint as to what form f should take. This thing is true. This inequality is true for every x, for every f imaginable. You can derive it using essentially a Fresnel conjugate for the minus logarithm. For those of you interested, there is a citation. You can read the paper. A more tighter version of this bound is called the Donsker-Varadhan lower bound, and it has this form. So basically, you can see that, you can convince yourself that this extra term here is bound on this logarithmic term here. That basically, the logarithm can be upper bounded by its argument -1. The f is called critic, and it's just a variational function. You can use any function, and for any function, this will be a lower bound. Of course, there exists an optimal function f, such that this lower bound actually coincides with the logarithm, with the divergence, with the Keil divergence. We'll see what this optimal critic is. But yeah, basically, this is a variational lower bound that you are supposed to maximize over f to get a tight estimate, a tight lower bound. And then there is another lower bound that has been recently proposed called the info-NCE. NCE stands for noise contrastive estimation. And it has this form that you have one sample from the joint distribution. One sample Z0 actually is informed about the x. It is dependent with x. And the capital K samples are sampled from the prior. They are independent of x. And then you just form this estimate here. F is the same as here, except since this one was in general Keil case, but this one is for the mutual information. So now we have to work with pairs of random variables, x and z, to estimate their dependence. So all these bounds, however nicely looking, will be shown to be very poor. And so the theorem that claims that this is the case has the following form. It's called the formal limitations theorem. Well, this is how I call it. Okay. And the theorem says the following. So suppose you have B. B is a function that takes in your sample, lots of samples, capital N samples, and some delta. And so what is this B is? Well, it's a high confidence distribution-free lower bound on the entropy. Yeah, we're talking about the entropy. Remember the first point from the TLDR section. So you want to have a high confidence lower bound on the entropy by essentially using only samples. You don't know the density, you don't know any actual probabilities, you only can sample. And so what this theorem says is that there is, if you have actually this high confidence lower bound, that B is smaller than the entropy with probability at least 1 minus delta over the draws of these samples x from 1 to n, then with high probability this lower bound B is upper bounded by something logarithmic in sample size. So you see this B is upper bounded by the entropy, which we want, but it's also upper bounded by the logarithm of number of samples, which means that if you want, if this entropy is high and you want to have a tight lower bound that is also large in value, then this thing has to be large in value. And the logarithm is known to be very slowly increasing. If you want this logarithm to be large in value, then the n has to be exponentially large in this value. And so this means that...
What you meant when you told that it's
yes.
more or less easy to estimate entropy when it has low values, but it's extremely high.
Yes. This is exactly this. This is exactly this result that says that if you want to have a black box, good high confidence black box lower bound on entropy, then it's gonna be exponentially expensive. Exponentially expensive in the number of samples you have to use, and equivalently in the amount of computation you will have to perform. Now, how does this relate to the mutual information? Well, at least in the discrete random variables case, you can. We know that the mutual information is upper bounded by the entropy. Remember that the mutual information is the difference of entropies, and the discrete entropy is non-negative. So this is exactly what's written here. So if the entropy does not allow good lower bounds, then so does the mutual information. Otherwise, you could use the mutual information to estimate the entropy. I should also tell a small disclaimer here that this is not my result. This is a result from the paper that has been submitted but not accepted to the ICLR conference. So given that, to the best of my knowledge, it's still unpublished, you should be taking this with a grain of salt. I tried my best to validate their claim and go through the proof of this theorem, but I can't say that I'm 100% sure that it's correct. However, there is still some other evidence that this result does indeed seem to hold. And I will show you how the three black box lower bounds I presented before actually, how this theorem manifests itself in these three lower bounds, how these three lower bounds are exponentially expensive. Okay, so let's start with the Nguyen-Wainwright-Jordan bound. Recall the bound has the following form. Then the optimal critic, the optimal function f, that you would recover if you were to maximize this right side with respect to f, would have the following form. It's just the logarithm of density ratios, the logarithm of b divided by the q. Now, if you well, of course, you can't integrate these expectations analytically. So what you do in practice is you form Monte Carlo estimates, since you only have samples, right? So you sample capital N samples from the P distribution, capital M samples from the Q distribution, and form the following Monte Carlo estimate. You can see that it consists of two parts. The first part is basically a Monte Carlo. So yeah, In this case, we're assuming that the critic is optimal. What I'm going to show you is that even if the critic is optimal, things are not great. Probably it's not much better when the critic is suboptimal. So when the critic is optimal, the first term, this guy, essentially is a Monte Carlo estimate of the KL divergence. And the second term, as you might expect, has zero expectation, but it has non-zero variance. And we'll see that its variance is actually the source of the problem. It contributes huge variance. The one reason for that is that, you see, the first term was operating in the log density spaces. The log densities are very nice objects. They are well-performing, and they usually do not vary too much. Whereas the second term operates on the ratio of densities. This is a very wild object. Whenever you see one in machine learning, you should be very wary of them. They might bite you with their enormous variance. Yes, indeed, you can show that if you write down the variance for the second term, then it's essentially the chi-squared divergence between the P and Q that has been divided by the number of samples, capital M. The chi-squared divergence has one particular property. It is lower bounded by the exponent of the KL divergence. So it's exponentially bigger than the KL divergence. It's a very fast-growing, quickly growing divergence here. So if we know that the variance is at least exponential, then that means that this term contributes a lot of noise in both directions compared to the first term. That means if you want to prevent the whole estimate to be deviating too much further away from the KL divergence, from the optimal thing, to ensure that the quantity is a lower bound, not an upper bound, that it is lower than the objective you're interested in with high probability, then you would need to use many samples to drive this variance down. You would like to drive the variance of the second term as much as possible. And well, this thing says that the number of samples, well, this is the only thing you can control here to drive the variance down. Then the number of samples has to be exponential in the KL divergence. This is the example of this exponential cost of good lower bound. So I hope I convinced you that the Nguyen, Wainwright, Jordan bound is expensive. Let us now move on to the Donsker-Varadhan lower bound. So it has the following form. It's very similar, except here you have logarithm. So now there is, let's just, the optimal critic is still the same. It's the same function, the same logarithm of density ratios. Now, let us just, again, since we can only use samples, let's just replace the expectation with the empirical expectation, the following form. Now, of course, you would notice and say that, well, wait a minute, this is not an unbiased estimate anymore. By the logarithm, the expectation inside of the logarithm prevents us from having an unbiased estimate. This is now a biased estimate, and by the Jensen inequality, you can say that this is an upper bound on this lower bound, but we don't know anything about its relation to the original KL divergence. It might be lower, it might be bigger. We can't tell for sure. We can't guarantee anything. But you can hope that maybe if you take many samples, then this thing will basically converge to 1 because of the law of large numbers, and the logarithm of 1 is roughly 0. So
no, it's not roughly 0. It's exactly 0.
In practice, it's roughly 0. so it's 0, and then you recover what you are looking for. So maybe if the number of samples is large enough, then these extra bias we are suffering from is not that great, and it's tolerable. So how many samples do we need? Well, bad news. Things of this form have been studied already, and well, basically people have shown that although the expected value of this quantity, the expected quantity of this bias, the expected bias, has the following form with respect to m, the following asymptotics. So it's decreasing as fast as the variance of what we have under the logarithm is decreasing. And as we know from the previous slide, it does not decrease fast. It takes exponential number of values, exponential number of samples, capital M, in order to drive it to 1 at least. So this hints us that this bound is not better, is not any better. It's also requiring exponential number of samples, otherwise we would be suffering from high bias. So the info-NC lower bound, it's probably the one easiest to show that it's upper bounded by the logarithm. You can basically do this directly. The optimal critic now has this form. It's slightly different, but since it's it's slightly different, but just because it's a lower bound on the mutual information and not the KL divergence.
And there are two types of variational parameters here, function f and k, right?
There are two parameters. The k is number of samples from the prior you're using, and the...
And for that case, the optimal f is the same.
Yes. So you can basically show directly that this lower bound is upper bounded by the log of number of samples plus 1. How do you do this? Well, it's very easy. You just move out the 1 over k plus 1 from the denominator. You get this term. And then what you are left with is the expectation, the exponent divided by the sum of exponents. This fraction that you are left with is between 0 and 1, so its logarithm is non-positive, so you can upper bound this remaining part by 0 and obtain the right-hand side. Once again, we have shown that this lower bound, interestingly looking lower bound, is exponentially costly when the mutual information is high. Here I plotted some toyish empirical comparison. In the green line here, I have the Monte Carlo estimate. So yeah, this is the one-dimensional problem of two Gaussian random variables that are correlated. And their correlation coefficient rho is slowly increasing towards the 1, so that the random variables are almost identical copies of each other, and the mutual information is high. So the dashed line here is the number of samples used to, the logarithm of number of samples used to estimate. The kind of threshold once you cross, once the true mutual information crosses it, you can expect the lower bounds to deteriorate. And this is indeed what we are observing. The blue line, the green line, the Monte Carlo estimate behaves nicely. It has a smallish variance. And when the mutual information is low, like less than 2 maybe, smaller than 2, then all bounds perform similarly, except maybe the info-NC, which underestimates the mutual information when there is no dependence. But as you increase the mutual information, as you increase the correlation coefficient, you see that the info-NC starts to suffer, well, fairly quickly. Once the mutual information passes the 2, the value of 2, you see that the deviation of the info NC bound from the Monte Carlo estimates starts to increase, and indeed the info NC lower bound never crosses this upper bound of log k plus 1.
And what about Wainwright Jordan?
Right. So for the Nguyen-Wainwright Jordan bound, you see that its variance is increasing. Well, it does not blow up right away, but you can see that here, well, if you look closely, that here its variance was mostly the same as the Monte Carlo estimate variance, but once the mutual information got bigger, then you see that the green shaded area here is much smaller than the blue shaded area. There is much more variance in the Nguyen-Wainwright Jordan bound.
So for random variables with a large variance of mutual information, we have either very biased estimators with low variance or unbiased estimates but with extremely large variance.
Yeah, that's right. Yes.
What is Monte Carlo estimation of what?
Of the mutual information. In this problem, I assume that I have, so for the mutual information, I had both all the densities, the joint densities and all marginal densities, so I can just use as a direct Monte Carlo evaluation of the chiral divergence.
Why then first blue bound is sometimes higher than at the real mutual information operation?
The blue bound?
Yes.
Well, because the NWJ bound is not a high confidence lower bound on. That means, indeed, the fact that it deviates, it exceeds the true value very often is a direct example of the theorem. You see that with high probability, well, quite often at least, you see that the estimate exceeds the true value. This is not something you would like to have.
Expectation exceeds 2 or not?
No.
No. In expectation, everything is fine.
What is about VD bound?
Yeah, I didn't draw it here, but it's well, surprisingly, it was performing even worse than the NWJ bound. I didn't fully understand why it was happening, so I didn't include it in the plot. Any other questions? Okay, now let's move on. But then one might question, wait, but these bounds have been used in practice to actually achieve some results, well, at least achieve the publications, right? The ultimate result of scientific. So why do they work? Well, when there is a theorem, how can it happen that there is theorem that says that they shouldn't work, and yet we see some papers actually being published with decent results? Well, there is another paper that's been out recently that has this name. It's also not peer-reviewed, and maybe some of you will be reviewing it. So well, the only thing I'm going to tell you is that in this paper, authors asked exactly the same question. Why do mutual information estimators, why do representations learned using mutual information maximization work so well when there is theorem that says you can't estimate mutual information reliably? Well, they provide several evidence, some evidence that the mutual information maximization perspective is not the right thing to do, not the right way to see these methods. These methods might be working for a different reason. And they show this by arguing that first, the tighter bounds, the ones with better critics, better Fs, do not translate into better representations. Sometimes you want to cripple your lower bound with the inferior critic with some bad function f in order to get good results. Then if you have invertible representation, then seemingly the mutual information has to be independent of your encoder, if your encoder is invertible, then it has maximum achievable mutual information with the original random variable x. And there shouldn't be any actual learning signal, because no matter which representation, which encoder you use, they all are invertible, and hence all information there has been already stored.
So this means that the mutual information is maximal.
Yes,
right?
yes. Although there is small technical detail, is that the maximal value of mutual information in continuous case is equal to infinity. Not a very good thing to work with. So what they observed is that if your encoder is invertible, then despite there being no good learning signal, no any meaningful learning signal, then the representations are still improving if you are training them if you are maximizing lower bounds to maximize the mutual information. Although it's already maximal.
No use to maximize mutual information itself. But maximization of its lower bounds somehow help.
Yes. Then you can also consider encoders that could be invertible or could not be invertible, that has this kind of ability to become ill-conditioned, to become less invertible in some sense, or harder to invert. And these encoders learned this way seem to be becoming ill-conditioned. They seem to be becoming harder to invert. And this is also this also does not confirm with the mutual information maximization representation. Ideally, we would like our encoders to be more invertible or easier to invert to preserve as much information as possible. So what they conclude with is that probably mutual information maximization perspective is not the right perspective on these methods. Probably these methods work, but for a different reason. They say that maybe it's the metric learning perspective that should be used. So I'm not a big fan of this paper, but at least the particular result that tighter bounds do not translate into better representation seemed to be interesting to me, and also it sort of confirms with the theorem. I like when things confirm with the theory. So, to conclude this section, I hope I convinced you that there are no high confidence black box lower bounds on the mutual information, but can we sacrifice something, one of these, in order to actually get good lower bounds? Well, I guess the only sane thing you could sacrifice is the black box assumption. Suppose you know something about the distribution, and it's quite often the case that you do know something about the distribution. What can you do then? This is exactly what we're going to do now. I'm going to introduce some what I call better lower bounds. So let's take a closer look at what the mutual information looks like. So it's the KL divergence between the joint distribution and the product of marginals, but it can also be expressed in this form, in more down to formulas form. These expected log joint minus expected log marginal of x minus expected log prior POZ. Now we can cancel some terms here. For example, in this way, we can cancel the log marginal on x here, and obtain the expected log posterior on z minus expected log prior on z. Or vice versa, since the mutual information is symmetric with respect to its random variables. You can say that it's the expected log likelihood, the conditioned likelihood of x given z, minus the marginal log likelihood of p of x. Now, all these quantities are full of intractable terms. We usually don't know these densities, but some densities are particularly hard to get. For example, in VAEs, well, you know this density, the log prior, but you don't know the log marginal, you don't know the log posterior, well, the same log marginal. So even if you are working in the VAE scenario and you want to evaluate the mutual information of your decoding distribution between latent representations Z and the actual samples X you get from the model, then you can't do this directly. There is always some intractable term that gets in the way, either the true posterior or the marginal log likelihood. So there are two ways we can evade the formal limitations theorem I have talked about before. We can either, basically the way we go and do so is by using some knowledge of the structure of the problem, knowledge of the densities. Then we can avoid lower bound in the entropy. Remember that the mutual information is the difference of entropies, and the reason the lower bounds we had before were so bad is that one of these entropies we need to lower bound in order to have a lower bound, right? So if we deal with one entropy directly and the upper bound, the one that comes with the negative sign, then we will have a lower bound. So yeah, this is one possible direction. So here I outlined two different but actually the same ways to circumvent the formal limitations theorem. Either we try to avoid lower bounds in the entropies, one of the entropies, or we're gonna use the marginal distribution in order to give a high confidence. We're going to use the structure of our problem, known densities, in order to give high confidence, not black box lower bounds in the entropy. So let's go with the first one. Suppose that we know the we will go with this definition of the mutual information. Here is the entropy of Z, and this is actually the conditional entropy of Z given X, minus conditional entropy. So we do not want to, we will not be lower bound in this guy. We'll be assuming that this marginal density is known, and so hence we can form Monte Carlo estimate of this entropy. And this one, the negative conditional entropy, we only need to upper bound it to have a good lower bound on the mutual information. And luckily, the upper bounds on the entropy are very easy to get. They are obtained from the cross entropy, the thing called cross entropy, and are basically derived from the following fact. Consider the Keil divergence between the P distribution, the intractable distribution that you can sample from but don't know its density, and some tractable distribution, Q, the one you know density of. So then this Keil divergence is equal to this guy, and by rearranging terms, by just moving the expected log P to the right-hand side, you see that the minus expected log probability of X is upper bounded by this thing. And here on the right, you have exactly the entropy. So the entropy is upper bounded by this, well, cross entropy, essentially. So by upper bounding this negative conditional entropy with cross entropy, one obtains the following lower bound, called the Barber-Agakov lower bound for the people who first, apparently were the first to introduce it.
Is it from my paper? dimension information yours estimate?
No. This is a very old paper from 2003.
Not so old.
Very extremely old. It's like a pre-deep learning area.
That's right.
The mine paper, the mutual information estimator, we're using the Donsker-Varadan bound. And
Different? I thought that they also just relied on that fact.
no. Their bound was not actually a lower bound. They had so they had an upper bound on the lower bound, so it's not guaranteed to be.
You sure?
Yes. Another possible direction, as I said, is to give a high confidence lower bound on the entropy, but to do so, we need to use some. We need to know the density. We need some structural assumptions, and we're going to go with the same structural assumption this time. We're gonna assume that we know the marginal distribution of z. So this time we're going to go with this formula. Again, it's the conditional entropy of x given z minus conditional entropy plus the marginal entropy of x. So it turns out if you know the prior distribution p of z, then you can have a good lower bound, good upper bound on the marginal log likelihood, and hence the good lower bound on the marginal entropy of x.
But why do we need to use lower bound if we know the marginal exactly?
Well, we know marginal on z, but not on x. We could use the approach from the previous slide, and one can see that they are actually the same. This is just another way to see the same bound, kind of the same. So those of you who have attended my talk last spring know that I have proposed an upper bound for the marginal log likelihood that can be generalized into this form. There should be. Oh, okay. Well, yeah. Well, it's okay. You can write rho hat here and here, but the KL divergence between the normalized and unnormalized distributions are not well defined. Well, wherever. So you can show that the log marginal likelihood is upper bounded by the following quantity. I don't think it's very illuminating as to what particular is going on here. It's just some mathematical formula. Don't pay too much attention to it. But what's important is that by putting it into this formula and combining with the rest, you can show that the mutual information, well, that is exactly equal to this guy here, can be lower bounded by the following expression. As you can see, there is only one place where we use the entropy, the distribution P of z. So we essentially this extra term here is the entropy, marginal entropy of z, and there is some extra addendum to it. Now let us look at this multisample.
Question.
Yes.
So this equation calls for any anomalized marginal densities, yeah? Joint densities.
So the rho hat here is a variational distribution that sort of approximates the joint distribution, and the Q is a normalized distribution.
Okay, and the second question, does this lower bound also bounded by some number like it was in previous section?
Yes, you can actually
Because
show.
There is the same construction.
It is similar construction, right? But so yeah, unfortunately, I don't have this in the slides, and well, this is great fault on my side. I should have included this theoretical analysis here as well. But you can show that this formula would need k to be exponential, not in the mutual information, but in the KL divergence between Q and the true posterior. Between the true posterior and Q. If the Q is equal to the prior, then you recover the info NC bound. We'll show this. I'm not going to show this, but I'm going to comment on that. So this bound can be made much better by learning an appropriate Q distribution. If your Q distribution is equal to the true posterior and rho distribution is also optimal, then you can show that the whole quantity will simplify down to this to the posterior, actually, to the P of z given x for any number of samples k. Any other questions? Okay, well, let us talk some more about this lower bound. It has this form, just to remind you. As it has been already said, the rho hat is meant to approximate the joint distribution, the unnormalized joint distribution over x and z. The Q distribution, well, it has to be normalized, and we also need to be able to sample from it. And it approximates the posterior distribution P of z given x. So now if we put k, if we make some choices, some particular choices in this bound, we recover some of the stuff we have been talking about already before. For example, if capital K is equal to 0, then the rows cancel out, and you're left only with the Q of z given x. This is exactly the Barbie-Ragakov lower bound I have shown you a couple of slides before. And the fact that the second term is the entropy of z, the marginal entropy of z, hints us that the first term is simply a fancy cross-entropy estimator for the posterior, for the log P of z given x. That is given by the thing called self-normalized importance sampling. So in particular, if you choose the proposal distribution, the Q distribution equal to the prior, and you say that the rho is equal to some learnable function times the prior, then all the priors will cancel out, and you will be left with exactly with the info NC lower bound. That will no longer be relying on knowing the marginal density, but will be exponentially expensive to be a tight lower bound. There is some relation to the semi-implicit variation of inference, but we are not going to get into that.
And I think the most important is the last line. So this unified model explains why info NC works so pure.
Yeah, kind of. Getting back to the empirical example we had before, this is the similar setting, but not exactly the same. So again, the dashed line here is the log number of samples, and the lower bound has been fixed for some particular Q proposing distribution Q. I didn't optimize it because in this case of Gaussian distributions, you can recover the true posterior exactly. The true posterior will be also Gaussian, and if I were to optimize this distribution Q over parameters over its parameters, then I would exactly recover the red line, the Monte Carlo estimate. Instead, I wanted to see how the bound performs for suboptimal, for fixed values of for fixed proposals. And here are three different choices. You can see that they all manage to evade this logarithmic curse and break this log number of samples threshold.
Well, it seems that just the threshold became a bit larger, but they still have some.
Well, yeah, they do. But as I said, it's now defined by how good your
Your Q.
posterior approximation Q. So basically, the whole thing of taking multiple samples gives you some additional bits. If your KL between the true posterior and Q is equal to, say, A, then you can reduce this A by log K bits if you use capital K samples.
Can we use some normalizing flow for proposal, and this will be quite good approximation?
Well, yeah, sure. You can, if you use some universal approximators for densities, then yeah, you should be theoretically able to drive this gap down to 0.
Why should you use Monte Carlo estimation for visual information? Can't you count it directly?
Well, it relies on these expectations, and you just can't.
In this particular experiment.
Well, yeah, I guess yes. In this particular experiment, I know what the actual mutual information as a function of rho is, as a function of correlation. But why I did a Monte Carlo estimation is to show that the variance of Monte Carlo estimate is, well, it's like the best thing you can achieve. So I didn't only want to show that the estimates are good, but also to show that the variance of these estimators is comparable to the best thing you can achieve using stochastic estimation. So yeah, you can, right, it's important to see that the confidence bars around these estimators are, well, not that greater and pretty much the same as the Monte Carlo estimate. Okay, so this concludes the lower bound parts. I hope this enlightened you in some ways as to what should we do when we seek to lower bound the mutual information. But as I said, sometimes you want to minimize mutual information. Then having an upper bound would be great, right? So again, let's for one more time see the definition of the mutual information. It's the difference of these entropies. And if we are now interested in having an upper bound, this means we need to upper bound the first entropy and lower bound the second entropy. Now, as we know, good lower bounds on entropies do not exist. So we would not attempt to lower bound the second term. Instead, we will assume that we know the conditional distribution of x given z such that we can estimate it directly. By just basically Monte Carlo estimating the first term here. And for the second term, we can come up with, we can use cross entropy estimates, since we need to upper bound this entropy. So yeah, this is what I have said. So the good multisample cross entropy bound on this entropy of x is given by the importance weighted autoencoders lower bound. So basically, you lower bound the log marginal distribution of p of x, and since it's taken with the negative sign, then you obtain the upper bound on the whole expression, right? So you end up with the following expression, which is very similar to what we had before for the lower bound, except this time the zeroth sample, the one that is actually correlated, that has been sampled from the joint distribution, is only used in the numerator and is not used in the denominator. Well, again, the Q is a normalized proposal variational distribution that we are supposed to minimize the right-hand side with respect to. You can put the Q distribution equal to the prior, and then you will not be needed to know the prior distribution. This Q and the prior will cancel out, and you'll be left with the conditional distribution P of x given given z k in the denominator. This is the case where you know the conditional distribution, don't know the marginal distribution, and well, there is something you can do, although this particular choice is likely to be a very poor one, much like the info NC lower bound.
Simple, strange question, but if you know the prior on the z and if you know the posterior on x, why don't just use one-to-power estimate?
Well, you can't. You see, you need to know distributions on the same quantities. If you have a distribution on x given z, then you also need to know the marginal distribution of x. If you know the marginal distribution of z, then you need to know the posterior distribution of z given x. Well, because the mutual information is expected Kl divergence, and Kl divergence needs to be operating in the same domain. See, so here basically, here it's written as the Kl divergence between the joint and the product of marginals. If you cancel out one of the marginals, then it goes in the conditioning part. Okay, so by combining the lower bound and the upper bound, one can get this nicely looking multi-sample sandwich bound for the mutual information. Looks very interesting, especially the fact that in order to make the bound tighter, you are supposed to maximize the lower bound and minimize the upper bound, and they are pretty much the same with respect to Q distribution, right? Very interesting detail. Oops. Well, so.
What about variance of the right of the upper bound?
Well, I don't have any analytical statements for that. Empirically, the upper bound is mostly IWAE bound, importance weighted autoencoders bound. And so it's the same cross entropy estimator. Cross entropy estimators. In the formal limitations paper I have mentioned, they have argued that just replace both entropies with cross entropies, and this will give you a good estimate. It will not be an upper bound or lower bound because it will be a difference of upper bounds, but it converges very quickly. It's hard to say what the bias is, but the convergence is like the standard for Monte Carlo, so they behave very nicely. They're basically based on the cross entropy estimator, which is widely used. All of maximum likelihood estimation is based on the cross entropy principle. So now the last part is that we have seen that the mutual information suffers from the fact that it's hard to reliably lower bound the entropy. So what the mutual information is, it's just the KL divergence between the joint distribution and the product of marginals. It's a very nice one, however, for one good reason. This one reason being is that the mutual information has very good, very easy to understand information-theoretic interpretation. It's very natural measure for the information between that one random variable has about the other. But if we forfeit this interpretation and just seek some measure of dependence of the form distance between the joint distribution to the product of marginals, then we can consider different distribution distances, divergences other than KL divergence. For example, one can consider the reverse KL divergence. The KL divergence between product of marginals and the joint distribution. one can go even more general and say, consider any convex function f such that f at 1 is equal to 0. Then one can define f divergence using this function f, and any f divergence will do. You can use any f divergence to measure the difference between the joint and the product of marginals. In fact, the reverse Kyle divergence and the original Kyle divergence are special cases of this family. Or you can use Wasserstein, say Wasserstein distance, any distance of non-distributions. In fact, people have already used this Wasserstein distance measure. This paper has been published at NeurIPS this year, so you can go and read it. It's more trustworthy, I guess, than most of other papers I have cited.
How was it called, this alternative information measure?
I don't think they, well, maybe Wasserstein mutual information.
Okay.
I'm sorry, what's an interpretation? Has to be from information-theoretic interpretation?
Yeah, the mutual information is difference of entropies. The entropy is a measure of uncertainty. At least in the discrete case, yeah, well, okay, let's go into this discussion. If your random variables are discrete, if your random variables... No, this is important. This is important. If random variables are discrete, then the entropy is finite. Then the entropy is very easy to interpret. It is indeed a very natural measure of uncertainty. However, if random variables are continuous, then the entropy, the differential entropy, can be negative. It can be infinite. This is very unintuitive. In fact, it's not clear if your random variables coincide, if x and z are equal to each other with probability 1, then if they are discrete, this mutual information has maximal value of entropy of x, which is very meaningful. If random variables coincide, one random variable carries as much information about the other as there is uncertainty in this other variable. This makes a lot of sense. However, if x and z are continuous, then this mutual information will be infinite if they are equal to each other, and this makes no sense. There is no infinite amount of information. Although, so maybe in the continuous case, we shouldn't rely on this information-theoretic interpretation. I don't think there is much of information-theoretic interpretation. In the continuous case, I think you are free to use any distance you want. So yeah, this is the discussion I wanted to have. But yeah, so in the discrete case, at least, these alternative divergences would lack information-theoretic description, information-theoretic justification, which is not cool. So I'm going to talk about one of these choices, namely the reverse Kyle divergence. That is given, so the mutual information is Kyle divergence between the joint distribution and the product of marginals. Let us see what happens when we consider a different order of arguments, Kyle divergence between the marginals, the product of marginals, and the joint distribution. This thing is called Lautum information. The Lautum is mutual spelled backwards. Very creative name. I like it. So it has this easy form. It consists of two terms. The one is the expected decoding distribution, the expected probability of x given z, that is expected over the product of marginals, minus the entropy of z, entropy of x. Sorry. So this first term is it's hard to deal with because it's basically a cross entropy on something. So I don't know how to reliably estimate it. But the entropy term, yeah, it does allow some bounds. Well, we have already talked about distribution-free upper bounds on the entropy and distribution not free lower bounds. We can use them here in order to estimate to have bounds on these low-term information. For example, the lower bound can be obtained using cross entropy. Remember, we have minus entropy on the previous slide. Well, this guy here is the minus entropy, so we can upper bound entropy with the cross entropy, and this gives us a lower bound. I guess maybe it should be called Barber-Agakov lower bound on the low-term information. You can use IWAE lower bound to have this kind of estimate, this kind of lower bound, the multisample lower bound. In the same spirit, you can use the IWHVA upper bound to have the upper bound that would have the following form. Yeah, so I guess that's it for the low-term information. It hasn't had much practical applications. There is like one paper that introduces the low-term information and one paper that actually tries to use it. And I think there is one paper by Daniel. Okay, there was at least an attempt by Daniel to put it to practice. So it's not clear how practically useful it is. In particular, it's not clear if this term has any meaning. What does it actually do? But at least it's one way to measure dependence between two random variables. So, as a pre-conclusion, I should say that well, basically, in these bounds we have derived, in these efficient bounds we have derived, we always relied on the a lot of the bounds were derived using the bounds on the log marginal distribution. So the log p of x. If you manage to estimate it to lower bound it, to have a good lower bound, then you obtain the upper bound on the whole mutual information. If you have good upper bound, then you have a good lower bound on the mutual information. What we've been using in this talk is this process called self-normalized importance sampling. But this is not the only way to get good lower bounds. So you can use the cross-entropy estimator, but this one will depend a lot on your choice of the distribution of Q. It has to be normalized. What if you don't have expressive normalized distribution? Can you improve it? Well, self-normalized importance sampling is one way to do so. But there are other approaches. For example, one can use annealed importance sampling. It's a much more complicated procedure. We will not be considering it in more detail, but at least it is possible. So basically, the self-normalized importance sampling, it tries multiple different samples and selects the best one. Whereas the annealed importance sampling takes whatever samples you have and tries to improve it in essentially using Markov chain Monte Carlo. And you can leverage power of Markov chain Monte Carlo, especially gradient-based Markov chain Monte Carlo, and have maybe even much better estimates. It has a lot of, it has a huge can of worms. It's tricky to reliably work, to provably work with Markov chain Monte Carlo, but at least it's a possible, promising alternative direction. One important difference, though, is that the self-normalized importance sampling is very parallel. As you have seen from the formulas, you just evaluate independently many different samples, and you can do this in parallel. You can leverage computational capabilities of modern hardware like GPUs to do this very fast. In contrast, annealed-dependent sampling is sequential in nature. Not only it uses Markov chain Monte Carlo inside, which is a sequential procedure, but also it defines a kind of path in the probability space that has to be transferred sequentially. So it's much less parallel and probably does not benefit from GPUs as much. So that's it. Let us recap what we have been talking about for the last an hour and a half. As was promised, I showed you that the mutual information is hard to estimate reliably, to lower bound reliably, because the entropy is hard to lower bound unless you're willing to pay exponential amount of computation. Actually, we have shown that the black box lower bounds on the KL divergence, the Nguyen, Wainwright, and Donsky-Varadhan lower bounds are bad. They require exponential number of samples in the KL divergence. If you actually know something about the distribution you're working with, say just one marginal distribution, then you can have much better lower bounds. Which is actually interesting. For those of you who are familiar with the concept of copula, you can realize that the copula is the object that contains all the information about the mutual information. The mutual information is solely defined by the copula of the distribution. And the copula is independent on the marginal distribution. So think of it. The copula is independent on the marginal distribution, and it is the mutual information is completely defined by the copula. And yet, knowing the marginal distribution changes something. It allows us to have much better bounds compared to the case when we don't know this marginal distribution. It's an interesting thought. So, the more you know about the distribution, the better it is. If you know the full joint, things are much better. We can have upper bounds, good upper bounds as well. You can have multi-sample bounds using this self-normalized importance sampling, and by using bigger number of samples, capital K. As an alternative to the self-normalized importance sampling, we've been using, one can use annealed importance sampling, although it's much more complicated. And finally, some people have started research into alternative dependence measures. Maybe they will be much more promising. In particular, those of you who are familiar with the Wasserstein GANs know that there are, in Wasserstein GANs, people have lower bounds on the Wasserstein distance, and this can be used as a lower bound on the Wasserstein mutual information. We don't know if they are efficient or not. Maybe they suffer from the same problem as the Nguyen Wainwright Jordan bound, but this it remains to be shown.
No, but I think this is exactly the content of this paper.
Well, they proposed the bound, but they didn't give any theoretical analysis, as far as I know.
And what about empirical results?
Well, they do have some empirical results, but as I said, there is empirical evidence for the... Yeah, as usual, I have blogged something, some more about this stuff. In particular, I have derived these AIS-based bounds. So you are encouraged to subscribe, share, you know, like, yep. All the standard stuff. That's it. Thank you.